To generate reliable grid-level power, modern utility-scale solar installations require absolutely massive tracts of open, sun-drenched land. Look at this desert array. Tracing the rows to the vanishing point reveals millions of individual, interconnected components spread across thousands of acres. This creates an operational paradox. The facility's massive energy output is entirely dependent on microscopic hardware connections that can easily fail under environmental stress. The industry identifies this vulnerability as Pao-Mao-Di-Lu, the cumulative minor losses that continuously bleed efficiency from the system. If 10 or 20 panels fail, the megawatt yield remains stable. But when thousands of these microscopic anomalies go unnoticed across a vast site, total power generation plummets. Operating a modern solar farm requires shifting focus away from simply installing more panels. The priority is mitigating invisible, localized failures across an expanse too large to monitor by eye. The causes of these localized failures are routine: a buildup of heavy dust, corrosive bird droppings, or internal microcracks can compromise a single cell. During a physical obstruction, the electrical behavior shifts instantly. A shaded cell stops generating power and becomes a resistive load. Instead of contributing to the grid, the compromised cell consumes energy generated by its healthy neighbors. This specific thermal reaction is strictly defined as the hotspot effect. The trapped thermal energy does not dissipate harmlessly. Over time, it permanently degrades the backsheet and encapsulation materials of the entire module. A single shaded cell acts as an active parasitic drain. It consumes adjacent power while physically destroying the hardware around it. To understand the scale of that power loss, we have to look at the series circuit architecture linking these modules together into long electrical strings. In a series circuit, total electrical current is constrained directly by the weakest producing cell in the entire line. This illustrates the barrel effect. An IV curve graph tracks current against a barrel with one short stave. Fluid fills the barrel and spills over the lowest stave, instantly flatlining the current on the graph. That short stave represents our resistive hotspot cell. A 5-centimeter shadow on one panel reduces the capacity of the entire string. It throttles the current for every single panel connected to it. Resolving the Pao-Mao-Di-Lu scaling crisis requires pinpointing and neutralizing these microscopic bottlenecks before they choke macro-level generation. The legacy response for finding these bottlenecks relies on ground personnel walking the rows with handheld infrared scanners. This operates on linear labor scaling. One technician can only scan a fixed number of panels per hour. That linear inspection rate directly collides with the exponential square footage of a utility-scale plant. Ground crews face severe logistical constraints. They must navigate difficult terrain, work around hazardous voltages, and contend with blinding glare. Because full site coverage is impossible, facility managers rely on reactive, sample-based checking. They inspect a small fraction of the site and hope it represents the whole. Relying on manual maintenance guarantees the barrel effect will persist. The math does not support ground-based diagnostics for modern solar arrays. To arrest cumulative power loss, facilities require a deterministic method to capture 100% thermal coverage at high speeds. High-endurance, enterprise-grade automated flight platforms provide the physical carrier for this operation. This false-color thermal image captures the output of the drone's radiometric infrared sensors. Against the cool blues of healthy panels, a single blisteringly bright yellow anomaly stands out immediately. Aerial radiometry visualizes the resistive heat of a hotspot instantly, entirely bypassing the physical line-of-sight obstructions that hinder ground crews. The drones operate on pre-programmed waypoint grids. This eliminates human piloting variables and ensures exact repetition of the flight path for consistent data. Aerial systems compress what would be a 3-week ground inspection into a single afternoon flight. The drone acts as a deployable, high-speed industrial sensor network that completely shatters the limits of manual labor. This split-screen map compares the final data acquisition workflows. On the left, a zigzagging human walking path. On the right, a rapid geometric grid over the same area. As the sweep concludes, precise GPS coordinates drop directly onto the bottlenecks identified in the thermal data. Operations and maintenance transitions from a blind, reactive search to a targeted, data-driven strike. By pinpointing failing cells early, crews neutralize the barrel effect across affected strings and restore full current to the system. Continuous automated mapping is the only mathematically viable method to eliminate the cumulative minor losses of Pao-Mao-Di-Lu. In the modern utility-scale landscape, maximizing grid power requires deploying intelligent aerial systems to defend the efficiency of the panels already in the dirt.